Okay, we move on to problem 8.61 of Sonntag, in which we have 1 kg of water at 500 degrees Celsius and 1 kg of vapor at 200 kilopascal. So if we have a chamber which is at constant pressure and it is adiabatic, process is adiabatic, so there is no heat transfer. Okay, so we have A as 1 kg water at 500 degrees Celsius and the mass is 1 kg and the pressure is given at 200 kilopascal. The other chamber contains saturated water vapor 1 kg H2O XB equal to 1 at 200 kilopascal. The process is a constant pressure adiabatic process. So from the mass continuity, after mixing, state 2 will have Ma plus Mb equal to 2 kg. First law is as follows: Q equal to M2U2 minus MAUA minus MBUB plus W12. Because it is adiabatic, it is insulated, this Q is equal to 0. So M2U2 minus MAUA minus MBUB, this represents the change in internal energy. So W12 is P multiplied by V2 minus P multiplied by VA plus VB. This is because the pressure is constant. So M2 U2, so this is equal to multiplied by M2 as well. So let me write this down properly. So the work done is equal to P times the total volume at state 2, which is V2 M2, minus the initial volume P V1 M1 VA MA plus VB MB. So if we recast M2 U2 and P2 V2 M2, it is equal to M2 U2 plus P V2 minus, we collect these terms, MA UA plus PVA minus MB UB plus PVB. This is equal to 0. So M2 H2 is equal to MA HA plus MB HB. This was obvious because it's a constant pressure process, so the enthalpy changes are locked. Okay, so M2 is equal to 2 kg, H2 is equal to MA is equal to 1 kg, MB is equal to 1 kg, which implies H2 is equal to HA plus HB by 2. So using the final enthalpy and the fact that state 2 is also isobaric, so P is equal to 200 kPa. Okay, for the state 2 also the pressure remains constant, and we have found out how the enthalpy will be. Using these two states we can find out whatever else is required. We should find out the final temperature. So final temperature is a function of the enthalpy and the pressure. Similarly the entropy generation, so S2 minus S1 times the, so for the entropy M2 S2 minus MA SA minus MB SB is the change of entropy, is equal to del Q by T plus delta S gen 1 2 between 1 and 2. This is 0 because it is adiabatic. So if we know the states 1 the state 1 is comprised of A and B. This A and B are the initial states, and state 2 is known because the pressure and the enthalpy is known. Then M2S2 minus MASA minus MBSB is equal to the entropy generation. So let's see how to do this in EES. So let me increase the font preferences. I prefer the Courier font for programming. Okay, so MA is equal to 1, MB is equal to 1, M2 is equal to MA plus MB. Okay, very good. State A, TA is equal to 500, MA, okay, MA we have already put down. P at A is equal to 200. State B is T of X B is equal to 1, PB is equal to 200. Okay, so HB is equal to MA times HA plus MB times HB divided by M2. So this is equal to H2. This is the equation that we had derived. Okay, H2 is this, where HA is the enthalpy of steam, T equal to TA, P equal to PA. HB is equal to the enthalpy steam at T equal to X equal to XB and P equal to PB. Okay, these two are mixing and giving us the final state. So let's see what H2 is. H2 is equal to 3097 kilojoule per kg. Okay, so once we have H2, we can find out, we can use the fact that the process is isobaric, so the final pressure is also 200. So T2 is equal to temperature or steam at H equal to H2 and P equal to P2. This will give us the final temperature. Final temperature is 312.5 degrees Celsius. So we have obtained the final temperature. Now this, everything that we derived here, everything so far is an application of the first law. We now apply the second law to find out the entropy generation. The entropy generation is equal to change in entropy, because there is no heat transfer from the insulated vessel. So Sgen 12 is equal to M2 multiplied by S2 minus MA multiplied by SA minus MB multiplied by SB. Equivalently, I can write this down as this. So this term over here is the entropy of the final state. This term here is the entropy of the initial state, which comprised of the two individual chambers. This is the mixed state. This is the entropy of the mixed state. This is the entropy of the individual states before mixing. So we must write down the expressions for the S of A's. So SA is equal to entropy of steam, SB is equal to entropy of steam at X equal to XB, P equal to PB. So ES is case insensitive, so it doesn't matter if the capitalization is missed. Similarly, S2 is equal to entropy of steam at X equal to H equal to H2 P equal to P2. This is because we must find out the entropy using the states of enthalpy and the pressure. Enthalpy and pressure act as the two parameters which characterizes the properties at that state. So the state is at H equal to H2 and P equal to P2. That gives us S2. So using this we can find out the Sgen. The Sgen is 0.2309 kilojoule per kg Kelvin. So Sgen is always positive because we know this from the second law. So the Sgen is always greater than equal to 0. It is equal to 0 for a reversible process. So this is problem 8.61. Try this problem out. It's a problem of mixing. The problem of mixing will be very useful for other chemical reactions and all those kinds of the studies which involve chemical reactions. So this is problem 8.61 of Sonntag. Okay.